Golden Iris Productions presents Was Einstein Wrong? Introduction to a Question That Still Shapes Physics by Mark F. Dennis. This is a question that sits at the center of modern physics. Was Einstein wrong? Not in the sense of whether his equations work. They do, with extraordinary precision, but in a deeper sense. What do those equations actually mean? And do they describe reality itself, or only the structure of how reality appears to us? Introduction. At the end of the 19th century, physics stood at a moment of extraordinary confidence. The mechanical picture of the universe appeared complete. Motion, force, energy, and light all seemed to fit within a single unified framework. It looked as though nature had been understood. But beneath that confidence, cracks were already forming.
Planck and quantization. Max Planck's work on blackbody radiation produced an unexpected result. To resolve the ultraviolet catastrophe, he was forced to introduce a radical idea. Energy could not be continuous. Instead, it came in discrete packets, quanta. Light, once understood purely as a wave, now showed a deeper duality. It behaved as both wave and particle, depending on how it was observed. Michelson-Morley experiment. At the same time, another assumption was being tested. Light, it was believed, required a medium to propagate. This medium was called the ether. But the Michelson-Morley experiment failed to detect any motion through it. No ether wind appeared, and with that, the idea of a universal medium began to collapse. Lorentz transformations. Hendrik Lorentz attempted to preserve the ether framework. He introduced mathematical transformations that explained how time and length would change with motion. Remarkably, the equations worked. They matched experimental results. But the interpretation still relied on something unseen, a background that could not be detected.
Einstein, 1905. Then Einstein took a different approach. He removed the ether entirely. Instead, he proposed two simple postulates. The laws of physics are the same in all inertial frames, and the speed of light is constant for all observers. From this, a new picture of reality emerged. A new reality. Space and time were no longer separate and absolute. They became interwoven. Time could dilate, lengths could contract, and motion began to shape the structure of space-time itself. What was once fixed became relative. Newtonian reality. Before Einstein, physics rested on Newtonian foundations. Space was absolute, time was absolute, and matter moved through a fixed and unchanging stage. Gravity was understood as a force acting at a distance. Everything had its place in a stable mechanical order. Energy in classical physics. Within this framework, energy was not a substance. It was a property of systems. It described motion, position, and change. Like the beauty of a mountain, energy cannot exist without the mountain itself. It is real, but not independent. It has no existence on its own. Breakdown begins. By the end of the 19th century, physics began to show cracks, not in everyday motion, but in the behavior of light and heat. small inconsistencies appeared that classical physics could not resolve. Ultraviolet catastrophe. One of these problems was the ultraviolet catastrophe. Classical theory predicted that hot objects should emit infinite energy at high frequencies, but this is not what is observed. Reality refuses to follow the prediction. Planck's solution. Max Planck introduced a radical correction. Energy is not continuous. It is emitted in discrete quanta. At first, this was seen as a mathematical trick, but it pointed towards something deeper. Nature was not smooth at all scales. Michelson-Morley result. Meanwhile, experiments failed to detect motion through the ether. Light behaved as if no medium existed. The concept of a preferred frame of reference began to collapse. Physics was entering a period of uncertainty.
Einstein removes absolute space. Einstein's approach was not to add complexity. It was to remove assumptions. He eliminated absolute space and time. Only relative motion remained. Consequences. From this followed time dilation, length contraction, and the relativity of simultaneity. Space and time were no longer independent. They depended on motion. Asteroids paradox. Imagine two asteroids moving toward each other. Each sees itself as stationary. Each sees the other as moving. And each concludes that the other's clock runs slower. This symmetry appears paradoxical. Key question. If both observers see the other as time dilated, what does time actually mean? Is it something physical? Or is it a relationship between observations? Mass-energy equivalence. Einstein's most profound result may be the simplest to write. E equals mc squared. Collapse of substance. Mass and energy are no longer separate. They are interchangeable. Matter becomes a form of energy. Energy becomes a form of matter. The distinction begins to disappear.
Interpretation shift. Physics shifts from objects to relationships, from substance to transformation, from things to structure. Final question. If space, time, mass and energy all depend on the observer, what is actually being described? Is physics describing reality itself, or the way reality appears from within space-time? Photon travel from a receding galaxy. Now consider a photon emitted from a distant star in a galaxy that is moving away from us. From the perspective of the star, the situation is straightforward. The photon leaves the star and travels at the speed of light towards the Milky Way. In that frame, distances are measured relative to the star itself, which is at rest. So the motion is simple. Light propagates outward at speed c towards its destination. But now we shift perspective to the Milky Way. From here, the entire galaxy containing the star is receding at a significant velocity. Yet the photon still moves at the speed of light. That speed remains constant in all inertial frames. Now the key point emerges. Both observers can calculate a halfway point in the photon's journey, but they do not agree on when that halfway point occurs. The timing is different in each frame. not slightly different in interpretation, but fundamentally different in coordinate description. And it goes further. Each observer also calculates a different location for that halfway point, because distance itself is frame-dependent under relative motion and Lorentz transformations. So the star frame and the Milky Way frame do not agree on where the photon is at the same stage of its journey. Yet both descriptions remain correct within their own frames. Both obey the same physical law: the speed of light is constant, and both are internally consistent. This leads to a deeper question. If time, distance, and even where something is depend on the observer's motion, then what is the photon's trajectory in any absolute sense? Is there a single underlying path, or only a set of consistent descriptions between frames?
How can this be? Clocks both fast and slow at the same time. Photons in two places at the same time. Photons in the same place at different times. These are the consequences of light being c for all inertial observers. This seems to border on metaphysical or mystical. Was Einstein wrong? Or are we still learning what his equations truly mean?